Okay, so we left off in here talking about whether a function is even or odd, right? And we described this with regards to the symmetry the graph may have. We said if we were symmetric with the y-axis, that function was considered to be even. And remember, when you're symmetric with the y-axis, your x-coordinate changes sign, but your y-coordinate does not, right? So evaluating with x produces y. Well, so does evaluating with negative x. It produces y as well. Okay. If you have symmetry with the origin, then you are an odd function. And the mark of an odd function, both coordinates will change sign, right? xy becomes negative x, negative y. The way the function notation works for this one, you're saying if you evaluate with negative x, that produces a y that would be the opposite as when you evaluate with positive x, right? That's how you'd read that notation, okay? So we did some tests down below, and now let's move to example 4. We've got a couple trig functions here. I already have them graphed for us just for the sake of time. And let's start with the sine function there. Notice that sine curve has symmetry with the origin, right? So we can say that this is an odd function. And I can, kind of prove that looking at a couple critical values here. So notice right up here at the top of the curve, that would be f of pi over 2. That's 1, right? Sine equals 1 at pi over 2. We'll notice down here at negative pi over 2, we're equal to negative 1. So we would say that f of pi over 2 is equal to the negative then of f of negative pi over 2. That's the mark of being odd. Evaluating with positive x yields the opposite as evaluating with the negative of it. Okay? And you can see, again, here's the symmetry with regards to the origin. Okay, next you have the cosine function there. It has symmetry with the y-axis, right? So we are even if we're working with the cosine function. Okay, notice cosine at pi over 2 is 0. That's because x is 0 at pi over 2. And at negative pi over 2, x is also 0. So those are equivalent, right? They are not opposites this time. They are equivalent, so we are even. All right, so then what about the tangent function? Even, odd, or neither? What do you think? Just by looking at the graph, you should be able to tell. Odd. Symmetry with the origin again, right? Okay, now some critical values you may want to look at. A good value for tangent is pi over 4, 45 degrees. So let's add that in here. That would be right about there. Tangent at pi over 4 is 1, and at negative pi over 4, we're negative 1. So we're opposites there. F of pi over 4 equals the negative of f evaluated at negative pi over 4. All right, moving forward. So now let's look at some specific transformations on some graphs here. Okay. So here I have the function f of x equals the absolute value of x squared minus 3. This is a tricky one. Really dial in on this one. Here's how I'm going to approach this. I'm going to first ignore the absolute value. I'm going to say, let's graph y equals x squared minus 3 first. Okay. And I'll just choose the following 5 integers to plug in. Okay, so negative 2, if you square that, that's 4. 4 minus 3 is 1. So we have a point of negative 2, 1. Okay. Negative 1 squared is 1. 1 minus 3 is negative 2. Got a negative 1, negative 2. 0 squared is 0. Minus 3 is negative 3. 0, negative 3. There's your vertex. Then we're going to get a negative 2 and a positive 1 again by some symmetry. All right, so there is your graph of the function y equals x squared minus 3. No absolute value, right? Okay, so now take into account the absolute value to graph this complete function f. So think you plug your number in for x, square it, subtract 3, and then the only thing left to do by order of operations is take the absolute value, right? So all of those values that I have in my y column there, I take their absolute values. So I get 1, 2, 3, 2, and 1. So I'm now going to have a point of negative 2, 1 on this graph of f of x, of negative 1, 2, 0, 3, 1, 2, and 2, 1. Go ahead and plot all of those. All right, so after we plot all those, you're going to be tempted to say, oh, well, based on the pattern of how those are kind of behaving, we're going to be doing something like that, right? Not actually the case. Okay, those critical values don't give me the full picture here. All right, here's what we got to realize. All of the y values that were already positive on the original function, they're going to remain positive, right? It's the negative values of the original function, y equals x squared minus 3. They're going to go from negative to being positive. Okay, so look at the blue curve. Where are the points of that curve already positive? Well, above the x-axis, right? So all of these points right here, they're going to remain where they're at. Their absolute values are not going to change, right? Same thing over here. Okay? So all of those points that I just highlighted in red are now part of this graph of f of x. And then the blue points that are left, that are below the x-axis, those are the ones whose y's change sign and go to being above the x-axis. So then that's where the rest of those critical points come into play. There is the complete graph of f of x. Almost looks like a W. So you got to be careful on the absolute value of a function. Be careful with that. We'll look at one more example here on the next page with that as well. All right, so click to that example. All right, so I have f of x already graphed here for us in red. Let's list out some of the critical points there on that graph. So we've got, looks like negative 4, negative 1, right? Okay, negative 2, negative 1. 0, 2 up here. How about we go down to 4, negative 2. And let's go one final one of 6, 0. And let's graph negative f of x next, the one that's in blue below this. All right, so you plug a value in for x. evaluate the function, get a y, and then you're just supposed to take the negative of that. That's what that notation negative f of x means. So I can use the same x values that I did in the critical points of the original f of x there. So if I plug negative 4 into f, I should get negative 1, but then I change the sign on it to being positive 1. Okay. If I plug negative 2 into f, I produce a negative 1, but then I change the sign on it to being positive 1 as well. If I plug 0 into f, I get a 2 by the red function, but that 2 changes to a negative 2, or negative f of x. If I plug 4 into f, by the red function I get negative 2, but then I change the sign on that to being positive 2. All right, and then if I plug 6 into f, I get a 0 out. Change the sign on 0, it's still 0. Okay, give me like 5 minutes. You just take one of those empty seats. All right, so describe what transformation just took place to go from the red graph to the blue graph there. What did we do? Yeah.
We reflected it over the x-axis?
Yes. This is a reflection over the x-axis. So just understanding the function notation, if I ask you to graph the negative of f of x, that just means you're changing the signs on the y's, therefore giving you this reflection over the x-axis. Okay? All right, now this next one is a little tricky. Let's go to the one up in green. We want to graph f of negative x. Okay? Well, I know here the input of this function is now negative x, and I know if I can get negative x to be the inputs of the original function that's in red, I can get the same outputs as red. So in my table here, in the middle column, negative x, I'm going to replace it with the same x values from the critical points in red. I know that if I can get negative x to be those values, then they're going to produce the same outputs that the function in red produces. Okay, so the question is, if I want negative x to be a negative 4 first, what does x need to be? It needs to be positive 4, doesn't it? If I put 4 in for x, it immediately turns to negative 4. Now I'm evaluating f at negative 4, which is negative 1. Okay, so what I'm going to do is then plot the point, the ordered pair that I plot would be 4, negative 1. Right there. If I would like negative x to be a negative 2, that means x has to be positive 2. So now I plot 2, negative 1. If I would like x to be 0, or a negative x to be 0, then x can still be 0. So I plot 0, 2. If I would like negative x to be 4, then that means x has to be negative 4. I would plot negative 4, negative 2. And if I would like negative x to be a 6, that means x has to be negative 6 initially. So I'd plot negative 6, 0. Oh, I plotted 0, 2 wrong, didn't I? Oops. Should be up there. All right, and notice that graph is a reflection of f, the red function, over the y-axis this time. So f evaluated at negative x, the x values are changing sign, giving you a reflection over the y-axis. All right, last one in purple there. So this is, we want to graph the absolute value of f of x, okay? So in my column, 3-column table here, I'm going to use the same ordered pairs from the original f of x. I know that negative 4 produced a negative 1, negative 2 produced a negative 1 as well, 0 produced a 2, 4 produced a negative 2, 6 produced a 0. That all comes from the original function in red. Now I take the absolute values of those. 1, 1, 2, 2, 0. Okay, go ahead and plot them. All right, and you're going to maybe be tempted to just draw something that looks like this. All right, connecting all of those, call it a day. Not going to cut it. Okay, those critical points don't show us the full picture. So we have to go back and we've got to look at the original graph in red there. All of the points whose y values were positive, which are these points, those are going to stay put. Okay, so I have to take that into account. That looks like basically from here to there and then all the way over to 2. All of those points are staying put. But it's these points here and here whose y values have to turn positive. And I would connect to give me the rest of the graph.